Let's consider convective mass transfer. Note that in the previous modules on diffusion, we have noted that molecular diffusion is quite slow. So to enhance transport of a component, we can use convection. Then the mass flux of that component will be higher. In other words, it will move at a faster rate. So we can have convective mass transfer in gases and liquid and also within porous solids. The convective mass transfer coefficient is given a symbol Km. M stands for mass transfer and K is the symbol for the mass transfer coefficient, and it is defined as the rate of mass transfer per unit area per unit concentration difference. So we can write that in a mathematical expression as Km equals m dot b divided by A times CB1 minus CB2, where m dot b is the mass flux of component B in kilograms per second, and C is the concentration of the component B, and that will be mass per unit volume, which is kilograms per cubic meters. And A is the area, or in square meters. So the units of Km will be, by substituting the units for the terms on the right hand side, we have kilograms per second in the denominator, square meters, and then kilogram in the denominator and cubic meter in the numerator. So kilograms will cancel out, square meter term will cancel out, so we are left with meter per second. So the units of Km are meters per second. We can get a better understanding of the mass transfer coefficient from its units, as we noted that the units are meter per second. We can also multiply both the numerator and denominator by square meters, so we have the units expressed as cubic meter divided by meter square per second. And then we can say that Km, the mass transfer coefficient, represents the volume in cubic meter of component B as it is transported across a boundary of 1 square meter per second. And so that gives us a little better understanding of mass transfer coefficient from its units. So we have Km equals m dot b divided by A times CB1 minus CB2. We can rearrange these terms as m dot b equals Km times A times CB1 minus CB2. Now you will recall from your perhaps first course of physical chemistry that for an ideal gas law we can write Pb equals rho b times Rb times T, where Pb is the partial pressure of gas B in kilopascals, Rb is the gas constant for gas B, rho b is the mass concentration of B in kilogram per cubic meters, and T is the absolute temperature. We can rearrange the terms as rho b equals Pb divided by Rb times T. Now note that the gas constant Rb can be written in terms of the universal gas constant as Ru divided by Mb. So Ru is the universal gas constant and Mb is the molecular weight of gas B. So we can substitute for Rb in our earlier expression. The mass concentration of B, rho B, equals Pb times Mb divided by Ru times T. Now note that rho B is the mass concentration of B, and earlier in our expression above we called the concentration as Cb1 and Cb2. So that's the same. The concentration is same as rho. So we can go ahead and substitute for that concentration terms in that expression, and we will get m dot B equals Km times A times the molecular weight of BMB divided by Ru, the universal gas constant, times the absolute temperature, and in parentheses now we have partial pressure Pb1 minus partial pressure Pb2. This expression is useful when we are trying to estimate the mass flux based on the vapor pressure gradient instead of the concentration gradient. So note that here we have the gradient expressed in partial pressures. We will use these expressions in solving problems where we are interested in finding out the mass flux.